Hello community! Today we talk about a GraphRAG optimization and in-context learning. And yes, we are trying to build the latest technology here. Maybe we go to a super GraphRAG and we want to improve here our in-context learning so we have a better performant LLM. Let's have a look what the latest technology is. Now, let's start at the beginning. We have in-context learning, we have RAG, and in both we can use here our knowledge graph. This is beautiful. So if you're new to AI, RAG is really simple. RAG stands for Retrieval Augmented Generation, so we have a retriever. So we build here with a transformer encoder, we build a mathematical vector space where we map the content of our text, the pre-training here, into a semantic embedding, a vector embedding. Oops, sorry, mistake. And this is it. Then we have the augmentation. So we augment here the user query here with all the relevant information that I got here from my retriever. And then we have the augmented prompt, and the augmented prompt is fed into the LLM. That's it. Now for in-context learning, and you see here in this visualization exactly where I place in-context learning in relation to RAG. Yeah, absolutely. So what we have a user query, and then now we are in the time of AI agents, provide now here agents the relevant information given the human query, and we have here a prompt optimization and agents that go out and provide all this relevant information for you. Of course, the core of those agents is a very dedicated LLM that has especially been trained on this, like we use here one LLM, our transformer encoder structure, a sentence transformer, where you can build your vector spaces of your domain with your pre-training data. And I have 7 videos where I show you how to build your own vector spaces free of charge. So you might say, hey, this looks similar, and look here where this visual simplicity takes place. Talking about simple, we just add a graph information. So we add here a knowledge graph structure. And we can add it here with in-context learning, where we simply have AI agents that act now on a graph, on a knowledge graph, and provide from this knowledge graph here, the agents come back and provide the relevant information that will help to solve my human query. The LLM is now provided here this complete prompt. But of course, we can also have here that now the retriever uses here the encoded graph information. Watch just out, because the more complex here in a RAG system the retriever becomes, the more you pay for external complexities by itself that are not related to the performance of your original answer generating RAG. If you have here an indexing, a re-indexing, if you have here a main retriever, then you have a domain-specific retriever, then you go with some re-retriever, you build up complexity outside of your main LLM that are just here to find information and make it real complicated to get the right information for your augmentation. And then, and this is what's the real powerhouse here, we are looking today now to optimize here the LLM or the agent here for in-context learning. And you see the in-context learning here and here, it is so similar from its functionality. Now, you might ask for video tutorials. Let's start here with the left side, in-context learning. And you might say, okay, to understand how this works, this is a video tutorial for you. His title is here, Harvard presents here a new knowledge graph agent, especially for medical AI agents. And here I show you how you interact with your medical LLM on a knowledge graph methodology invented and published by Harvard. And you have all the links in my video. If you want a video tutorial that explains here the knowledge graph and the RAG system optimization, easy. Just take this one here, just from some weeks ago, where we worked together here on a knowledge graph-driven RAG system, and I showed you 4 methods plus a new method, and in this video we explored here a similar graph RAG methodology, where you do not have to have any additional training, but you simply have a knowledge graph-based RAG, SimGraph RAG. So you see, you can go both ways if you want to add here the knowledge and the information and the deeper data structure from a knowledge graph. If you want in general more video tutorials, no problem at all. Here I show you exactly how to add a large language model to a knowledge graph given the new GIF methodology by University of Berkeley. Here we go with Stanford, and as you can see, automatic scientific discoveries through multi-agent intelligent graph reasoning, Stanford versus MIT. They are competitive methodologies. You can choose what you like. And of course, we built multi-agent system. I show you here in this video 7 AI agents and a knowledge graph, and the methodology is called Agentic Graph. So you see, you can go and have a knowledge graph adaptive reasoning where you plan here your agentic system on a graph knowledge manifold. Or if you want, you just decode on graph. So you empower your large language model with a knowledge graph, a methodology invented by MIT called DOG. There are so many methodologies that you can choose from, and I want to give you some amazing literature. Yes, let's focus here on GraphRAG. This is your publication, the very last day, 31st of December 2024, Retrieval Augmented Generation with Graphs. And here you have it all. Michigan State University, University of Oregon, Adobe, Amazon, Meta, Snap. You have here some beautiful, comprehensive and up-to-date survey on GraphRAG methodologies. So whatever you want to know, I think this is the latest, just 7 days ago, published. So you have here all the information, and you have, as you see in the last line here, a GitHub repo where you find, for example, exactly this here. So you see, if you want to specialize on all the different methodologies for a knowledge graph, you just go there and you have the paper, you have the code if you want immediately implement this. And if it is an open source, you have the code and you just click on it, you git clone your GitHub, and you can run here with this new methodology. So real nice, but you think it's only a knowledge graph? Oh no, because this nice repo here, you see, graph-rag, GraphRAG. This is your GitHub. If you go down, you scroll down, you have tabular graphs. You have here the paper and the code, and all the different methodologies. Infrastructure, RAG, graph-based explainable prediction. You have this for traffic networks. You have this for scientific networks, for a biological graph, the paper and the code. And I think this is really, I had a deep dive here. This is really perfectly if you want to start or you want to specialize your GraphRAG to your domain, to your complexity, or you simply want to try out a new GraphRAG methodology. You have here more than 80 different versions just waiting for you with the code. They did a very intelligent segmentation because they say we see the GraphRAG in general as a 5 core component structure. And they identify here the query processor, the graph data source, the retriever in itself, then the organizer, and the generator. So really simple but a powerful representation that you can scan immediately to the complete world of GraphRAG. In general, I think this IR, this information retrieval, will continue in 2025 to be really an active area of research. And you see it here, just January 3, 2025. Here you have also from university very interesting ideas about biomedical knowledge graph, where you augment this and you have a multimodal, which is really interesting, contrastive representation learning now on those graphs. So the graph, some people say graph is not really anymore now with agent one of the most important tools that we use within AI. I think this is not the case. Graph are really important. Graph have, especially biomedical knowledge graph here, you see a lot of research done in medical, especially on those type of knowledge connectivity. And here, if you want here the pre-trained models and the data, you have here the GitHub repo for you if you want to have a deeper look. So we have domain-targeted knowledge graph like biomedical and the integration of AI agents now on multimodal data. And I think they are still a hot and a current topic of research. Graphs are important. Because if you look now at this paper, you see exactly, you have here your biomedical knowledge graph, you know the attributes, and then you have your pre-trained language model. You remember the BERT model, the sentence transformer. And we have now a new BERT. We have the modern BERT. I have a video on this. So you can here even get a better performance out here before you have the attribute embeddings. Then you have the classical contrastive learning. And then you do, like years ago, the link prediction on the knowledge graph embeddings. I think I have 5 or 7 videos on this. Just search on my channel. And you see, then you have the input, an incomplete graph, relational graph convolutional network encoder, and output is a completed graph with the predicted connections on a molecular level. Therefore, I think graph really important with the embedding, with agent. It will be a powerhouse. Coming back now to a very simple representation of in-context learning and graph, I tried to explain to you that they are not really that divided anymore. And here, just 2 days ago, here in my posts, I told you, in the old days, and it means a year ago, you had the knowledge that in-context learning was more or less with examples that were static, predetermined by humans, and RAG was more or less information was only factual, documents, articles, or database entries. Now, a year later, this is not true in any way with this AI, dynamic AI agents. This is not anymore true. But if you go and ask, for example, your, GPT-4, or you go even to O3 and you ask this, you will still get the old knowledge. Because interestingly, some of our huge LLMs, they have a knowledge cutoff somewhere at the end of 2023 or the mid of 24. So even our AI system don't know about this and still reference here old, outdated information. Great. But you know what? Let's go a step further because we want to get better. We want to improve. And yeah, I showed you here GraphRAG, but let's go another step. So if we have now the complete system of in-context learning with the agent feeding in the relevant information here for the augmented prompt, which we feed to LLM, and let's say, okay, we have a retriever, and hopefully you do not pay for a commercial vector store, but you build your own vector spaces for free for your domain-specific knowledge with a simple SBERT model, with a simple transformer encoder. Then you might ask, but what is the complete performance of the system? What is the output performance if you say, okay, this is it, and now show me the result? Which system is better? But you know what? The main question is not, is in-context learning better than a RAG system? But the main question is, how good is the quality of this LLM, the training of this LLM, the optimization of this LLM? And how can we do this? It is so easy. You just say, hey, both get here the same user request and the same relevant information. So what we do, we eliminate, if you want, the problematic externality from this retriever or the performance of the agent. We just say we start here, we have a query, and we have relevant information, and then we just test out which LLMs have the best performance. So we just ignore, if you want, the first step here. So this was done. So we have a defined user request, our query here, and a full document, which I call relevant information to solve the query with, and now we go with a maximum length of 32,000 tokens. Now this is important because in my last video when I talked about here long context length with 2 million token, a lot of you replied, hey, from Anthropic, I only have 128k token. And I think this response is general. You want to be able to break it down because only Google has now these real multi-million token models. So this was done here at a context length of only 32k tokens. So more or less every modern LLM is now in this test range. And I think this is a fair condition. Evaluation. As I told you, requiring long-form responses. So you don't want to go for this simple, immediate answer, but you want that it is really here outputting a little bit more of a complex reasoning structure, not the simplest answer possible. So the long-form responses are required to be fully grounded in the provided context document. This is our relevant information. So there is the solution. But now the LLM getting the query and the relevant information has to find here in these 32,000 tokens the relevant information while fulfilling the user request. And if it finds it, it must find this information that is really able to solve the query, because just finding something that is not helpful for answering the query is also a disqualification. So we want a real result. We want a real answer given by our LLM, and I think this is a fair test. And here we have it published today. This is here the 7th of January 2025 by Google, and they have brand new, for me, I record this today on the 7th of January, the facts grounding leaderboard. And this is exactly what I just told you. They limit the long context here to 32K tokens, requiring a little bit what they call long form now within this scope. And they say, listen, we provide here a new leaderboard for everybody to test out, and you can run this on your preferred LLM. So you have immediately your test and your comparison to those that are published here on Kaggle by Kaggle. It's called the Facts Leaderboard, and just to show you, they have, of course, here a lot of questions here, and so this is the domain distribution of their query, and this is the task distribution. So, facts grounding leaderboard, there's quite some chunk financial domains, internet and technology domain, the legal, really important, medical, the dominant sector, medical, and then retail or product specific topics are here, just 11%. And now for the task, so they really divide this up, and you immediately see where, in what task category your LLM will shine. So we have everything from concept comparison, explanation, effect analysis, find and summarize, or some fact-finding task, or summarize and simplify the text, or just summarize and format, and you got the idea. So I think it's quite a fair distribution in our test data set, in our test queries, and here you have now one of the first responses. Of course, we have judges that judge this. And here, in whatever pink this is on your screen, you see here the judge models. And I think Google was quite fair. It went with its own Gemini, okay. Then it went here with GPT-4 Omni from OpenAI, and then from Anthropic, Claude 3.5 Sonnet. Open and blind test. And then they say, adding all of this together, average. And this here is now currently on the first day, so this is pre-filled by Google. You see here the rank 1 to 9. So at first, Gemini 2.0 Flash Experimental, Claude 3.5 Sonnet, GPT-4 Omni, GPT-4 Mini, OpenAI O1 Mini, OpenAI O1 Preview, and then given here the specific votes by the specific AI judges, you have here the average value. Now if you go to Kaggle, and this is a screenshot here by Kaggle today, so day 1, if you go there to the leaderboard, this is it currently. So this is here, as I showed you, 1 Gemini 2.0 Flash down to O1 Mini. So if you have your particular LLM, go there, you will find there the test, you run the test. I will run the test for 2 of my models. Maybe I will not publish then the result on Kaggle, but at least then you know how good your models are on this particular task that is so important for in-context learning, for the RAG performance, and even for the GraphRAG performance, regarding here how good is the LLM in the input of the augmented information. Now, if you're really interested into this, and this is now for nerds only, January 6th, so yesterday for me, revisiting in-context learning with long context language model, KASTE and Google DeepMind. So there's now this new, and of course it's coming from Google because Google is here leading this long context language model. And if you see LLMs, now you know what it is. And they test it out now, and they want to know how to get the best result out of in-context learning. Up until now, we had a lot of RAG, but now let's focus really only on in-context learning. And those long context language models have here raising an important question of whether ICL performance in a many-shot regime is still sensitive to this classical method of sample selection. You have some few short examples, and you carefully craft those examples to be really spot on your task. Now, if we look at this, and this is not for the easy of heart, so you see exactly what they do. They have here the number of examples and the performance of the system, and they do this for different tasks. They do this for an average summarization, for an average translation task, for an average reasoning task, and an average classification task. And you see here, given here, the performance for different topics. And this is interesting because I learn here it is not the same performance for everything. Summarization has a different effect than translation. I'm looking here for reasoning, not so much for classification, but you see there is something going on we have to understand. But of course you might say, hey, these were clear data, but we have real-world noisy data. Google took care about this also here with the noise ratio now on the x-axis. You see here the performance, and again for the summarization, the translation, the reasoning, and the classification. And you see, given for different translation, or even look here in orange we have archive, and here in green we have the government reporting. So it is interesting, even if you have a highly specific, let's say in theoretical physics or in organic chemistry or in mathematics, you have a real specific scientific terms that you use. No? So even if you add 40% of noise, you are still relatively good because the system seems to understand what is noise and what is here real scientific information. If you go in more, let's call it general government reporting structures, maybe for a broader element of the society, you see a complete different behavior just for the job of summarization. Reasoning is also really interesting. Look at the green line, look at here the orange line. There are some inherent differences that are really interesting to explore and understand when to apply what. But let's make it general. This is what I would say. We have a shift, a core shift, and we go now from an ICL sample selection procedure to a context utilization that is much broader. Why? In my words, I think there was the old paradigm, yeah? With the older language models and the limited context window, like, I don't know, I remember 8K. The focus was heavily on optimizing now specific examples to provide within the in-context learning. So choosing the right few examples was seen as critical for the performance here of in-context learning. Now, the new paradigm with this long context language model with 2 million token, 8 million token length, now we have this kind of massive context windows. And they changed this. And now this particular research, if you have a deep dive, please read this publication, this preprint. It's really interesting for your particular topic. They tell us, hey, those carefully selected examples generally do not provide significant benefits over random examples when you have enough capacity. So they say the main challenge is no longer finding here the optimally designed and crafted few short examples for in-context learning, but instead, now that we have, I don't know, give me the first 500 examples, effectively utilizing all that expanded context space. So this is interesting. It doesn't mean, hey, wait, it is not valid anymore to have a few beautiful examples. But if I have the chance to provide 500 in-context learning examples in one prompt, I can have a huge variety of topics I can cover, a huge variety of complexities I have in these 500 examples. No? I really can play around, and not every one of those 500 examples has to be perfectly designed and perfectly crafted for the ultimate experience. I can let them be generated synthetically by another AI. And yeah, I think this is the point now. Not carefully selected 1, 2, 3, 4, 5 examples, but now I have the place to 4, 5, 600, 2,000 examples. And here really utilize here the complete context space. Go with whatever cross-domain, inter-domain, crazy application you want. We simply have the space for this. And the question is now, is the result now better if I go crazy and have 500 examples? Is there a benefit in the performance of the LLM? And now, this is now my personal summary. This is not anymore by Google. This is now my reflection, how it will reflect and impact my work. And I will use this here for the augmentation prompt for my RAG systems. I go with CAG systems. But it is also valid for the optimization of the results returned by the RAG retriever. And of course, in-context learning. So I think I will make something different, because this implies that the model learns well enough when shown a sufficient quantity of diverse examples in the prompt, making now complicated selection and pre-selection unnecessary. So the implication for me is you can simplify your SCL setup. Just a basic random sampling methodology or sampling strategy is sufficient. Just make sure you have a real diverse set of examples, but you don't have to take extra care of the perfect setting. And this makes sense, because if you go for the high quality RAG retriever requests, some of the RAG retriever requests that you retrieve the 2000 closest references to your query embedding in the vector space. This is an extreme amount of retrieval data, of retrieved token that you have to pay for if you go for a commercial RAG retriever. But they say, yes, we need this because after the RAG retriever, then we have a different indexing and a different multiple LLMs that further optimize these 2000 examples, because they know the retriever is not able, if it would only sample 20, that in these 20 we find relevant information. So this now somehow makes sense if I see now this impact from in-context learning, from the augmentation. Just give me sufficient quantity of diverse example, and they don't have to be top-notch quality. Which is interesting, but let's try that. Second, so when the available real-world examples for a task were limited, the context window might not be fully utilized. And Google says here, we propose augmenting now. You have the place in your prompt with synthetic examples, since they do not have to be top-notch quality with the highest complexity levels. So you can go with synthetic examples that you can add so that you have enough training data. Interesting. So this augmentation methodology now led to a significant performance improvement in their tests by Google, filling now the context window with more relevant information. So this means if you only have, let's say, just an idea, 50 examples for your few-shot in-context learning, go to your LLM, say, hey, look, those are my 50 examples, synthetically generate another 50 examples that are real close here in the semantic, in the structure, in the form, but just generate more of this. And since, you remember, we don't have to go for the top-notch designed prompts, this shows here, the Google results, significant performance improvements. So if your domain training data suffer from a lack of training data, use here data augmentation by another LLM to fill here more of this large context of your LCLMs. 3, but careful, there is a point of diminishing returns. So don't fill it up to 2 million tokens. This doesn't make sense, no? So while more context generated leads to improved performance, so the more example you provide, the better will your performance get. However, there is a plateau. And eventually, even the system performance will degrade as the context length approaches here, let's say, the 2 million token limit of the model. So don't go to the absolute extreme of the 2 million, but let's say, I don't know, maybe 100,000, 200,000 token is already enough. Maybe you need 1 million token, great. But remember, there are diminishing returns. So even if you add another 100,000 tokens, maybe your performance will only increase marginally. So trade-off between context length and performance when you start to plateau in your performance indicators. Point 4. Those LCLMs exhibit a good resistance, especially if you are in a very specific, highly specialized domain knowledge or a knowledge graph, good resistance to noisy example within the context. As long as the proportion of those noisy examples is rather low. Now, if you, however, have to go here to some general text, please remember that you should definitely use, this is an implication that I will use here, filtering strategy to only keep data that provide here some positive and some correct influence. Because if the noise gets too high, there are for a particular task in particular domains with particular models, my goodness, there are particular thresholds. And if you're over the threshold and your data is too noisy, the LLM will not get it. The performance of the LLM will degrade. And the last point 5, this is really, I don't know if I really go with this. I have to do my own test with this. But according to Google, the ordering of the examples in the ICL input context does not significantly influence the performance of the response of the LLM. So I learned with pre-training that the phases of the pre-training, it is important the ordering of your data. But now Google tells us here with in-context learning, on the Google model specifically, given their specific training routines or whatever, the ordering of my few short examples in the in-context learning prompt, if I have an LCLM, it does not significantly influence the performance, which is nice. Because I started with rather simple examples and then increase the complexity of my examples step by step, the more example I provided. So I started real simple and I got more and more complicated in the build-up of my example in the in-context learning prompt. And now Google tells me, you don't need to do this. I'm not convinced yet. I have to run my own test, but if you know this already, hey, I would appreciate a feedback from your side on this topic. Okay, I think this is it for today. Very short. What is the latest technology from this week here on GraphRAG? Super GraphRAG, 70, 80 different implementation on GraphRAG. Papers and code available for you to test out and understand that the RAG system is real similar, especially if you look at the augmentation to the in-context learning, that they are interconnected. And I think the only critical element in a RAG system is that somebody thinks here, if you go for here commercial retriever system with commercial vector store, there can be some extreme prices if you do not have the knowledge to build up your own vector store and your own vector embedding. But I think it is so easy. I've given you now so many possible ways to build this. I think if you are a small startup or even if you're an independent developer, you do not have to pay here this sometimes extraordinary prices here for commercial retriever models. Great. So this is it for today. I hope you enjoyed it. I hope you had some new ideas, maybe some new literature. And if you subscribe, it would be great to see you in my next video.